Oh my goodness. Ba 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 ba. Okie dokie. Let's see. That's ready to go. Okay. Good morning, Tyler. Alrighty. So I have set up shop in Ridgecrest right now. So hooray. Yucky smoke for everyone. Sucks that we get it all, huh? Even though there's nothing like burning super close to us. Alrighty, so today we are going to. Oh, so by the way, I did put some like PowerPoint stuff in. Yeah, I know. Yeah, like even out here, it's just gross. It's orange and brown. Oh. I put some PowerPoint stuff in Discord. We're not going to use those, thankfully. I'm not a fan of PowerPoint, but they're there if you want to use them as a resource. The information they have is still, good. So you're welcome to use those as a study aid. And if you do find them helpful, my friend did send me like all 12 chapters of lecture notes. So if you do find the PowerPoints to be a useful study guide, just let me know. I'll put them all up there if you guys want to use them. But just remember that I'm only going to test you guys on stuff that I specifically cover. So maybe there might be a couple things that either I cover in more detail here or less detail. So just keep that in mind. Yeah, I know. Disgusting, disgusting fires. Oh well. So cool. Okay, so we are going to start our next topic. By the way, did anybody have any questions about naming? Are there any, like on the nomenclature worksheet that I gave you guys for homework, like any outstanding questions that are troublesome that maybe you can't figure out? If there's anything like that, we can address it now. Otherwise, we'll just go ahead. Oh, I know, the smell is horrible. Yeah, it's awful. I guess I'm glad like the house here doesn't have a doggy door, so like I can just close all the windows and like crank up the fan to make sure that it's going through the filter. But like yeah, as soon as I open the door to let them out to use the restroom, man, it's just awful. Stinks. It's like irritating my throat and everything too. So yep, but oh well. We have to all deal with this crap. So we should all just buy air purifiers and, give them all our money and survive that way. But we'll deal with it. Okay, cool. Remove, I don't know, pretty much all of California. Well, I guess everything's cheaper elsewhere, right? So that's your other option. Okay, so we're going to be talking about chemical reactions today then. There you go. Just evacuate while you can. So, you gotta do what you gotta do. Alrighty, chemical reactions. So, these are going to be, if we were to define these, chemical changes, right? We're going to be converting one substance into a different substance. Or multiple of each, of course. We're going to have reactants turning into products. And this is kind of just the general idea of a chemical reaction. We're going to be reacting one or more things to produce one or more products. Right? So an example of this might be something like taking hydrogen and burning it, turning it into water, for example. This would be an example of a chemical reaction where H2 and O2 are reactants, and water is the product. Okay, so hopefully there's nothing too new with that. What's also important in a chemical reaction is that the mass on the of reactants, if I can spell, is always equal to the mass of the products. So we cannot just like come up with we can't just say, okay, I'm going to put I'm going to mix a cup of flour and a cup of water. Okay, those aren't really masses. Okay, I'm not going to mix a pound of flour and a pound of water and somehow get 3 pounds out. Like, does not work that way. If you're going to put, a pound of whatever with a pound of whatever, you should get 2 pounds of it, right, at the end of it. So this is something called the law of conservation of mass. And you've perhaps heard this before, where we can say matter cannot be created or destroyed. Or destroyed. Don't know why I used quotations and then the parentheses. There we go. So we can't just, nothing is going to get lost and nothing is going to just poof out of nowhere. So if we put together, 10 grams plus 25 grams, and we got, say we had 2 things turning into 2 other things, we could say we could figure out the mass of the last one, right? Just by understanding that the stuff on the left has to equal the stuff on the right of your arrow. So if the stuff on the left was 35 grams that we put in, we better get 35 grams out. And if one of those things was 12 grams, then the other one is going to be 23 grams of whatever. I could throw chemical substances with these, but the idea here is that whatever you put in, you should get out again. Okay, so that's first thing. We're going to have a few type of reactions we're going to discuss this chapter, and there's going to be a few that we're going to discuss in the next chapter. For whatever reason, the textbook does not group them together, so we will, I guess, deal with them separately for right now. So we're going to be talking about 3 different types of chemical reactions right now, and then we're going to discuss another 2 in the next chapter. So we're going to have a few types of reactions. The first one is going to be a synthesis reaction or a combination reaction, in which you take 2 things and stick them together. For example, that could be hydrogen and nitrogen combining together to make ammonia. Or something like sodium plus chlorine turning into sodium chloride. So, pretty easy. You'll stick them together. If it's a metal and a non-metal, I would be expecting you to be able to figure out what the product is. But if it's something like nitrogen and hydrogen, since there's multiple things that those can form, I'm not going to ask you to calculate that. So if I ever give you, for example, let's do potassium plus phosphorus. I don't know, I'm just coming up with ones. If I were to ask you what this would be, you would use the preferred charges of each one to figure it out. So you would say, okay, well, we know potassium likes to be +1, phosphorus likes to be -3, so we should get K3P, potassium phosphide, at the end of it. Okay, so I could ask you to figure out the product of a synthesis reaction. Are you guys getting an echo right now? Oh, shit. Okay. So we had this problem in the morning that just went away by itself. So we can hope that just happens again. Yeah, I do have... Yeah, the wind sounds... that's just my laptop fan, so... I don't have my normal setup because unfortunately that computer doesn't have Wi-Fi. Stupid. I could go out to Walmart and buy a wireless card, but I'm like, whatever, I have this laptop. We can make it work. So, we'll deal with it. Sorry. Hopefully, by the way, the internet did come back last night. Like, as soon as I got to Ridgecrest, I was like, okay, we're back. So, didn't quite need to be here yet. So, I do actually like living here more. Just tangent time. It is quieter, and I like how big the roads are and everything. It's really nice. I love it, but I don't have any furniture really yet, so kind of sucks. Los Angeles, so just a few hours south. So I would just go up and down as needed. But so here I have a bed and a table. That's all I've got. So I don't even have a fridge here. So yeah, LA is pretty smoky still right now, also. But I guess I just have a better filter there or something, so I don't smell it as much. So, but yeah, so and I don't have an office here quite yet either because this is my first semester at Sarcoso and everything's blown up because of COVID. So normally I would be like, okay, sure, I can go stream there and I have everything set up and it would all be nice. But anyways. Let's continue with chemistry. So, yeah. So again, yeah, hopefully the echo will go away. What I did last time, I shut off, the desktop audio. I muted this laptop, and I muted the other computer as well. Hopefully that'll fix it, but we'll see. I do have my normal mic here. I can try and hook that up tomorrow. But this was kind of a last-minute thing, so we'll see. Okay, cool. Any questions on synthesis or combination? So that's just two things coming together to make a different thing. Okay, that's good. I think the fan, though, is going to be pretty much constant, so hopefully that's not too, the whoosh in the background is not going to be too bad. But we'll live. We'll survive. The second one is going to be the opposite, decomposition. Alrighty, and that is going to be some sort of compound turning into two things. For example, we might have calcium carbonate turning into calcium oxide and carbon dioxide. That would be an example of this. We could also have another one. Mercury 2 oxide turning into mercury and oxygen, something like this, or another one, hydrogen peroxide, turning into water and oxygen. So we can have all sorts of different things here. I'm not going to make you memorize any of these types of reactions. These would not be as easy to predict for us. And typically for these to happen, you have to have some sort of you'd either heat them up, or with the peroxide, you could give it a catalyst to help it happen. But typically these are less common. But they are another type of reaction. So I would expect you to be able to identify a decomposition reaction by understanding it's one thing breaking down into multiple things. And that's kind of as far as that's going to go. Okay, and then the third type we're going to have here is going to be combustion, which is typically going to be something that is a hydrocarbon, as in something that is made of carbon and hydrogen, plus oxygen burning to produce carbon dioxide and water. So, for example, that could be like methane, or, sorry, I meant to do that in blue. Oh well. Propane, the same idea. You always get carbon dioxide and water as your products. We live in chemistry here. We live in an ideal world. We don't have carbon monoxide or like just soot or anything happening. We have happy pure reactions where we always get carbon dioxide and water. So this would be a combustion reaction. Occasionally, less common, in green here, you might have a combustion reaction where you have oxygen as part of your hydrocarbon as well. This is totally a possibility. For example, if you were to burn glucose, that's what the C6H12O6 is, if you were to burn that, you would get carbon dioxide and water. It is also combustion. Combustion is also just kind of burning. And so if you're ever given something that's a hydrogen, carbon, and oxygen, you better put the products as carbon dioxide and water. Alrighty, so those are our three reaction types so far. And now let's go ahead and put in that pesky law of conservation of mass that we saw before. So if we go back to one of those synthesis reactions that we had here, we're going to notice that this is unbalanced. If we think about it, we have on the left side, we have one sodium and two chlorines, but on the right side, we have one sodium and one chlorine. So this reaction is not balanced. It is not obeying our law of conservation of mass, so it is currently not quite complete. So what we're going to have to kind of do is, for the first couple of these, I'll put up a table. Yes, Kevin, we know you know the answer. Come on. Very good, though. If we have a little table, we can do that. We can say, okay, we have one sodium on the reactant, two chlorines on the reactant side. We have one sodium on the product side, one chlorine on the product side. And we can say, okay, how are we going to fix this so that the chlorines are balanced? We have to turn this guy into a 2, right? And how that's going to work is we are going to basically take our sodium chloride and have 2 of them instead. And as a result, we're now going to have 2 chlorines on the right side. However, what we also need to know is by doing this, we're also going to have 2 sodiums on the right side. And as a result, we're going to need to adjust the sodium on the left so that it matches the amounts of sodium on the right. These things are called coefficients. And technically, the coefficient in front of chlorine there is going to be 1. So we know that we have 2 atoms of sodium plus 1 molecule of chlorine turns into 2 units of sodium chloride. Do the same thing, could balance another equation. we can go ahead and throw together our little table. Sodium and chloride back again, huh? All right, we have 2 and then 1 and 3. So looking at here, it's not as obvious to us, but we're going to use kind of that same idea from before with charge balancing. We had to find the least common multiple. So how are we going to get 2 and 1 to work out? Sorry, let me use green again. I like to just go top to bottom, but you can do it in whatever order you want. If we want these to be equal, we're going to have to stick a 2 in front of ammonia. Doing so is going to bump our hydrogens up to 6. And if we need the hydrogens to also be equivalent, we have to adjust the coefficient in front of hydrogen to make it balanced. And we should always double check, okay, we have 2 nitrogens on each side, we have 6 hydrogens on each side, we are good. Alrighty. Any questions on those two? Okay, so far so good, I assume. Let's up. How about we do this one? Let's do. Let's make this a little bit more complicated for us. So, in this case, we have 3 elements. We have our reactant side, product side. 3 hydrogens on the left, 2 on the right. We have 1 phosphorus on the left, 4 on the right. We have 4 oxygens here, and it looks like we have 11 total oxygens on the right. We had 10 from the first compound and 1 from the water. Looking at this, we can deal with the hydrogens first if we wanted. Why not? Let's go ahead, make them both 6. If we do that, we're going to bump our other ones around. We're going to just have to make our adjustments. 10 plus 3 is 13. Wow, that was more hard. Why did I have to think about that? Okay, so hydrogens are done. However, phosphorus looks like it's still not balanced. So let's go ahead and bump phosphorus up to 4. Doing that, it's going to mess up our hydrogen and oxygen. Sorry, I'm just going to cross those out because I did not leave myself enough space. 4 times 4 is 16. We can go back and now mess with our hydrogens again if we wanted, or we could go to oxygen, but hydrogen is probably a little easier. If we want to make that one into 12, we're going to have to make 6 waters instead. And lo and behold, that is going to make our oxygens equal as well. One thing I would suggest on something like this is do oxygen last. Because in this case, oxygen is in both compounds in the product side. And so it's going to be more complicated because we have 2 compounds to mess with. However, hydrogen and oxygen, there were only, or hydrogen and phosphorus, they were in separate compounds, so they're easier to work with. Okay, so for something like this, I would suggest working with oxygen last. However, you are totally welcome to balance these in whatever way seems best to you. Alrighty, any questions on that? If not, we shall continue. Into the world of, hey, that's awesome, Shane, I'm glad to hear. So go figure, I did nothing. So, who knows? Alrighty, our next one. Reactants, products. 3 elements here. I'm just going to start this off, 4 and 2, and then 2 and 3. Okay, so just like before, carbons are already balanced. Let's move on. We can go to hydrogens. Okay, we're going to need 2 there. I'm sorry, that's not what we need. We need 4. And if we're going to adjust the number of waters there, we're going to have to adjust our oxygens. I'm sorry, I should not have erased that. 3 turns into 4, right? We have 2 oxygens from carbon dioxide and now 2 from 2 waters. And looking at this, we're going to need, oh my goodness, we are going to need 4 oxygens to balance it out. And that one's done. Hooray. So notice if you started with oxygen, you might have been tempted to say, okay, we have 2 and 3, let's make those both 6. But that would be troublesome because you would not know how to divide the oxygens up on the product side very easily. So again, I would suggest doing oxygen last here. Okay, we're going to see combustion reactions are always kind of a pain to deal with. Alrighty, so it looks like we have some confusion. Okay, let's address the... So Shane, yes, that one, the phosphoric acid one, was more complicated than the first ones we did, just because we had oxygens on both products. The combustion reaction is a little bit more complicated. And let's see, where are we confused with this one? How did 3 turn into 4? Okay. So, let's do this in, I'm going to use purple for this and orange for water. Okay? So, originally, we had 2 oxygens, plus 1 oxygen from the water, right? And then we made this one into 2, right? We added an extra water to balance out our hydrogens. And so as a result, this thing went originally from 3 to 4. So we had oxygens from both carbon dioxide and water. And so we have to take account of both of those. So that's where that 4 came from. Okay, because we did not mess with carbon dioxide in this particular problem. Does that answer the confusion a little bit? I hope it did. Because we're not done, we're going to keep doing these. C2H6 plus oxygen. More complicated this time, though you'll see why in a moment. Reactants, products. We have 2 carbons, 1 carbon, 6 hydrogen, 2 hydrogen, 2 oxygen, 3 oxygen. Ethane indeed. So let's go ahead and start as normal. First thing, we can mess with our carbons, make our carbons equivalent. Doing so, we now have 4 oxygens from CO2 and 1 from water. So that is 5 put together. Okay, again, that's 4 from CO2, 1 from water. If we go ahead and mess with our hydrogens, oh my gosh. We want our hydrogens to be equal. We're going to have to put a 3 in front of water. And let's adjust our oxygen again. We have 4 plus 3 now, which is 7. And so what we're going to have to do is be like, oh crap, how are we going to get this even number of oxygens to be an odd number of oxygens? For right now, the answer is, let's just try and make that 7 by doing something naughty. If we put 7 over 2 as our coefficient there, in front of oxygen, we can make it work, right? It's going to be disgusting. Nobody likes to see it this way. But we have a way of making this work out a little bit more cleanly, right? What we're going to do is we're going to multiply everything now in our reaction by 2. So this is yucky. When we're balancing reactions, we want to have integer numbers. And so it is the devil's arithmetic, I know. It's naughty. We could have made it 14, as you'll see, which will work as well. But what we're going to end up getting is 2 ethanes plus 7 oxygens turns into 4 carbon dioxides. Sorry, just trying to keep our colors consistent here. Plus 6 waters. So notice, all I did between these two things was multiply everything by 2. All right, just to get rid of that pesky fraction. So I just multiplied all of these by 2 to get rid of it. Whenever you have a fraction as a coefficient, you want to get rid of it. So that's when you're going to want to multiply. Typically, that's only going to be 2. There are not a lot of triatomic elements. I can't think of any, actually. You will see a lot of diatomic elements, like oxygen. You can multiply by 2. One thing, by the way, if you want to cheat and not have to worry about this, if you start by doubling your reaction, you can avoid the whole thing. I can do another example where we do that. So we needed our oxygens to be 7 on both sides, right? We had 7 oxygens on the right. We needed 7 on the left. If we were to make them both 14, that would really be a problem because we would not know how much to give to CO2 and how much to give to water. Like, it's not obvious to us how we should split that up. So the best way to do it is to just make that oxygen on the left side have a fraction without messing up the rest of our stuff. But yeah, we'll do more examples of this. Okay, so if you don't want to see the fraction ever again, just multiply everything by 2 at the start. So let's just do that now so we can see. So if we have, not plus. Let's go ahead and just put everything as a 2. And by doing this, we are going to eliminate that problem of having a fraction later. Okay, you do not have to do this. If you are comfortable with the fractions, by all means keep them. Don't confuse yourself. So anytime you see a combustion problem, you could just double it at the start. And as a result, we're going to see reactants products, carbon, hydrogen, oxygen. We're going to have 8 and 2. Hydrogen, we're going to have 20 and 4. Oxygens, we're going to have 4 and 4 plus 2, which is 6. I don't know why I wrote it 4 plus 2. Oops. 6. And so look here, because sometimes, yes, sometimes you may have to use a fraction. Typically, if you have an element that is diatomic, meaning it occurs as a pair always, like oxygen always comes as O2, whenever you have stuff like that, you may need a fraction. So that may be one thing to do. Yeah. So, but notice here, previously we started with an odd number of oxygens. We started with 3 oxygens, right? And that's going to be a pain because our oxygens always come in pairs. So so by doubling it, we've made everything even, and that's going to make our math a little bit easier. Okay, so let's just go ahead and balance this from this point. Now that we've already doubled everything, let's go ahead and balance. So we want to make this guy have 8, right? Oops. So let's just cross it off. Okay, 8. 8 CO2s. So now let's go back, evaluate our oxygens again. We have 16 from CO2 plus 2 from water. 16 plus 2 is 18. I'm sorry, I should not have erased that. Hydrogens now. If we want to get to 20 hydrogens, that means this is going to need to be 10 waters. And so now we're going to have 16 oxygens from carbon dioxide, 10 from water. That's going to mean we have 16 plus 10, 26. I can't do simple math, guys, only complicated math in my head. Okay, and now how are we going to get oxygen to be 26? Well, that's simple. We just make this one be 13 instead. And now we have 26 oxygens. Poof, we're done. Okay, if you did not start doubling, you would have 13 oxygens on the right, 2 on the left. So you would put 13 over 2 as your fraction, and then you would double everything and you would get the right answer. Same way. Is this okay? So hopefully this is a little bit nicer than having to use the fractions. If you just double it at the start, you can kind of bypass that whole thing automatically. For the last one, you mean? It is that way. We did get that. 2 ethanes plus 7 oxygens, 4 carbon dioxides, and 6 waters. Yep, just a different problem, I know. These all look the same, right? It's all just a bunch of C's and H's. Totally. No, don't be sorry. Yeah, I totally get it. Like, you were working on the previous one, and here I am just zooming ahead. So you're 100% right. You did it correctly on your own. Alrighty. Shall we do one more? You guys... Oh no, the echo is back, huh? Oh well. Sorry. Hopefully it's like not too bad. Like as long as you can still understand, I guess you'll survive. Alright, do we want to double this one at the start? Excuse me. Sure, why not? Combustion reaction, go ahead, double it. If you want, you don't have to. Remember, it's your choice. But I just want to show you an example if we start doubling it in this case. Okay, carbons. 6, 4, no, that's not right. 6 and 2. Hydrogens. 16, 4, oxygens, 4 and 2. Why can you double combustion? I mean, you can double any reaction. Go right ahead. No problem. However, it's probably not going to help you with other reactions. Doubling it from the start makes you avoid having to use fractions sometimes. Or rather, okay, let me try that again. Sometimes combustion reactions, when you're balancing them, you will need to use a fraction. Doubling it at the start eliminates that need. So for some people, it is easier to do the math for. Some people, it's totally fine to use the fractions. So totally your preference. But if you do not like fractions in your balancing, go right ahead, double it every time. You will still get the right answer. Okay, and Satori has done this for us, which is great. 6. So she's done, or he, I don't quite remember. Oh well. Let's make this one 6. And then we're going to make this 16, so this is going to be 8. Our oxygen is 12 plus 8 is 20. And so this is... Oh, I'm sorry, not. That's going to be 10, right? No, 20 because the 10 goes here. Yeah. And so, what Satori has noticed is, hey, all of these numbers here are divisible by 2. When we are balancing the equation, we always want the lowest possible integers. I mean, technically, it is balanced as we have written it, but if we wanted to be more correct, we would say, okay, all of these are divisible by 2. Sorry. And we would want to reduce it. 5 oxygens. So in this case, we would not have ended up with a fraction. But again, if fractions scare you and you don't want to ever deal with them, go ahead, double at the start. Sometimes you might have to divide by 2 at the end. That's the trade-off there. So it's either deal with fractions or potentially have to divide at the very end. So pick your poison, whichever way you like. Sometimes you may have to do it. Okay? And so even though the top one is technically correct, if I were to ask you on an exam, I would expect you to write the bottom equation. Okay, so just as good practice, we will want to have the lowest integer values for our coefficients. All right, how was that? Any questions on the balancing? The good news for you is I have hundreds of these you can practice with. So, of course, I'll be giving you homework, but I also have a website that you can just practice balancing on, like over and over and over again. It's a self-generating type of quiz. Like, You just tell it, okay, give me 10 balancing questions, and you'll balance them, and it'll tell you if you're right or wrong. Yeah, so you just want to look. If we look at the coefficients for the top equation there, we see that they're all divisible by 2. So we should divide by 2. So it was just like a quick glance. You see, okay, these are all even numbers. Yeah, so I mean, you just kind of take a look at them. Typically, the only thing you'll need to divide by is 2. So as soon as you see an odd number, chances are you probably will not need to divide, but double check anyway. So, yeah. So if you were to look at the last one, you see, okay, 2, 13, 8, and 10. Okay, none of those are divisible by the same number, so we leave it as it is. We see 13 is also a prime number, so that tells us right away that we don't need to divide anything. We see we had 7 in the one before that as well, so we don't have to divide. Okay. Other questions on balancing? No, you don't have to do a chart. Totally. You could, if you like, I can show you a different way, which some people like. Some people it will just confuse them. So maybe I shouldn't show you. You can come up with a system of equations that you can solve to get the coefficients every time as well. That'll always work. But yeah, you do not need to show your work like this. So whatever way works for you, that's great. Maybe if you want, you can share your method in Discord. Like if you have an easy way of sharing it, maybe some of your fellow students will find that way a little bit easier than dealing with a chart like this. So that may be something helpful to other people. So if you want. Cool. Any other questions? Trying to think here. I don't know if I want to start the next kind of section here right away. It kind of is, it's not directly related, but let's not. Okay, so today I guess we'll just end a little bit early. Yeah, exactly. You guys can deal with this. You can practice your equations. So I'll put the practice thing up so you guys can mess with it if you want. If you're so bored that you feel like practicing your chemical equations. And tomorrow we will start a kind of different topic. Okay, so as requested, I will save this one as, I guess, balancing chemical equations. That was kind of the meat and potatoes of what we did today. So we'll put that up there. Okay? Yeah, I'm going to put it in a Canvas and Discord for you guys. Okay? So give me a little bit to put that up. You know what? Let's see. I have to find it. Let's see. I'll find it later. I'll do it off stream. But I'll put it in both Canvas in our extra resources tab, as well as on a Canvas. Did I just say on Canvas for both of those? I meant Discord, the extra resources, and then in Canvas as well. It'll be obvious where it is. Okay? So what I'm going to do, Karen, is I'm just going to upload the keys because it would be a huge pain for me to mark all your stuff and put them back, if that makes sense. If you could imagine printing out 60 people's homework, writing on it, rescanning it, and sending it back to them. No, not going to work. So I'm just going to upload the keys. You guys will kind of check your own if you had questions on any of them. So sorry, Karen. Normally, if this were, a class where you turned in a paper homework, I would totally have written on it and given it back to you guys, but just way too much effort right now. So sorry. Okay, cool. So I'll upload that. I will see if I can upload it today. I hope I have them on this computer. Otherwise, I will have to rewrite them and take pictures or something. So we'll get that up to you. Okay, cool. So with that, enjoy the rest of your day. Stay safe as always. Stay indoors, as much as possible, and enjoy. So I will put practice up for you guys. Have fun. Take care.